All right, so Zoom decided to stop recording halfway through that, so I guess I'm doing this in two videos. Okay, so we just finished face processing and object recognition. So the next thing we talked about was hemisphere specialization. There we go. I just put everything onto one slide here. So most of the research in hemisphere specialization is with epileptic patients who have had their corpus callosum cut. They'll do that so that the epilepsy can't spread from one hemisphere to the other, and they can retain some semblance of a kind of a normal life. So it's a really effective treatment, and this also opens up the opportunity to study individuals who have no corpus callosum or have a cut corpus callosum. And so if we use our visual pathway knowledge, knowing that the peripherals will cross to the opposite hemispheres, as well as which hand is controlling which hemisphere and that sort of thing, we can study each hemisphere independently. So left and right visual fields cross to the opposite hemispheres, and also the left hemisphere controls the right side of the body and the right hemisphere controls the left side of the body. So we learned a bunch of things using this method. So we found that language has some differences between the two hemispheres. That is that the right and left hemisphere can both comprehend language, but the left hemisphere is the only one that can produce language. When we look at visual spatial tasks like orienting things in space, we find that the right hemisphere is very good at it, but the left hemisphere is impaired. So using just your left hemisphere is very difficult to do any sort of spatial relation tasks. We also found differences between the ventral and dorsal pathways between the two hemispheres. So the right hemisphere seems to be involved in global, larger, kind of big picture sort of object recognition in the ventral pathway, low spatial frequency information. So again, big global ideas. And then left hemisphere is involved in the small details. So small local, small parts of what you're looking at are processed in the left ventral pathway. Looking at the dorsal pathway, we find differences as well. So again, dorsal pathway is the where pathway. We're looking at spatial relationships. And so the right hemisphere seems to be involved in distances between objects. We call that coordinate representations. And then the left hemisphere seems to be involved in relational information. So left, right, front, back. So the couch is left of the table, that sort of information. And then we moved on to attention. So attention has two components. It both selects relevant information and also inhibits irrelevant information. So you have a huge amount of information that's coming into your brain. Attention comes in and selects the stuff that's relevant to you and kind of inhibits everything else. So it's a really important process, important function of the brain to limit the amount of information that we're using for behavior. So we split up attention into kind of 4 different ways of thinking about it. You have voluntary versus reflection. So voluntary attention is when you're using your current goal to direct your attention. So I need some coffee right now. I'm going to direct my attention to the coffee mug over here and drink some coffee. Reflexive attention, on the other hand, is unconscious. So it's like if something jumps out at you, you can't help but pay attention to it. Reflexive attention is just any time that you're not using voluntary attention. So if I'm just thinking about something else and I'm just doing something like eating or something like that, I'm not particularly thinking about it, that's all done through reflexive attention. Okay, so anytime it's unconscious. And then you have overt versus covert. So that it just has to do with where your eyes are. So overt attention is when your attention is on the same location as your eyes. So I am paying attention to my coffee mug right now, and my eyes are on it as well. So both are in the same location. Covert attention is when my eyes are in a different location to what I'm paying attention to. So I might be looking at my coffee mug, but I'm actually paying attention to my laptop. So my eyes are in a different location than my attention. Then we talked about early versus late. So early attention is when you are looking at attention selection early in perception. Late is selecting information after perception is already done. So here in early, you could say, okay, attention is going to come into V1 or V4 or even early temporal lobe before the processing is done there. And that is all considered early selection. So attention is coming in and selecting those low-level features. And so there's quite a bit of evidence for early selection. So the Posner spatial queuing task, as well as the EEG version of that task and fMRI, all show that activity is not only, so attention is selecting things not only early in time, but also as early as LGN in the visual pathway, which is extremely early. So a lot of evidence for that. Late attention, again, is once perception is already done. So you go through the ventral pathway, do all the processing. Now I recognize what I see. I have the semantics being the meaning behind what I'm looking at. So there's a lot of different visual information coming from this coffee mug, and then eventually I will recognize it as a coffee mug. And so late selection attention is when attention comes in and selects it after that is already done. I've already recognized that I have my coffee mug, or that is a coffee mug, and it is selecting that information and using it that way. Okay, so either during perception, that's when attention comes in, or after perception is done, I already know what I'm looking at, then attention will come in and select the information. There's only one piece of evidence that we covered for late selection, and that is the Stroop task. And that shows that attention is still active after perception is already done. So it looked like attention is getting affected by late selection or late semantic processing, suggesting that attention is still active basically throughout the entire perceptual practice and after. Okay, so that's early versus late. Then we talked about feature versus conjunction search. So this is really talking about how many features are different between a target and a distractor in a visual search paradigm. So visual search is just like Where's Waldo? You're just looking for something in an array of other things. And then when I'm talking about my target, I have some sort of target that I'm looking for in Where's Waldo? It's Waldo, that's your target. And then distractors are all the other things, the things that are not the target. So if there's only one feature difference between my target and my distractors, that is, I have a green object in a field of red, right? One feature being color here. That green thing will always pop out at me no matter how many red things I put on the screen. So as I add more and more red on the screen, green is just as easy to find. So the reaction time, or RT on this slide, will not change no matter how many items I add. Okay, so it just kind of pops out at me no matter what. So it's all parallel. It's done entirely parallelly. We don't have to look at each item to see if it's actually the target or not. Conjunction search, on the other hand, we have multiple features that are different between the target and the distractor. So now maybe I have color and orientation. So I'm looking for a green vertical bar among red and green horizontal and vertical distractors. Okay, and so now that I have two features, now suddenly, as I add more and more distractors, it takes me longer and longer. So that's a really stark difference compared to the feature search paradigm, right? So I only added one more feature, and now suddenly it's taking me longer and longer as I add more. And so conjunction search seems to be serial. It's like we have to pay attention to every item on the screen to see if it's our target, whereas that's not true in feature search. So feature integration theory is a way, or is a theory that or was trying to describe or trying to answer the question for why. Why is there a difference between feature search and conjunction search reaction times? And so the idea here is that attention is necessary for binding features together. So in perception, we know that the features are split up into different areas of the brain. So we have like color goes to V4, orientation stays in V1. So they're in separate locations. And feature integration theory suggests that you have to pay attention to the object for those features to bind together in that object. So if I want to tell if something is a green vertical bar, I have to pay attention to it, bind those features together into one object, and then decide, is that the target that I'm looking for? Right? So if there is a green horizontal distractor, I have to pay attention to it, bind those together. Then I know that it's the wrong one. Then I have to move my attention to the next thing, bind those together, so on and so forth, which is why that as I add more and more distractors, it takes longer and longer for me to complete the task. It takes me longer and longer to find the target. There are other theories, that's just one, but I found it very powerful. Another really great reason why feature integration theory was so prominent was that it answers the binding problem. So the binding problem is actually an object recognition problem. And it's the problem that, yeah, we know that all of the information gets split up into different regions in the brain, right? We take that in and then we split it up into V1, V4, MT, right? All of that information gets split up. How do we put all of those back together to form what we consciously see, which is a full object, that doesn't have different pieces floating around in different locations and that sort of thing? Somehow we got to bind all of that together. And feature integration theory suggests that it's attention that's doing it. That attention is going to come in and take all of that information from the different parts of the brain, bind it together into one object perception. Okay. Excuse me, I have a bit of a runny nose this morning. Okay. So now spatial neglect. So spatial neglect is a neuropathology that is the inability to pay attention to something, but is importantly only a deficit in reflexive attention. So if you remember, I mentioned that reflexive attention is not only when something is jumping out at you, but it's also the attention that's kind of used for things that you're not really paying it full attention to. So like when you're eating, occasionally attention will go down to moving your spoon to the food to grab it and maybe paying attention to different parts of the food and that sort of thing. But you're not conscious of it, right? You're thinking about something else, right? You're thinking about your exam coming up or something like that. Sorry to stress you out. And so it's not voluntary attention. So spatial neglect is a lesion in the parietal lobe that gives you, or that makes it so that you cannot have reflexive attention for one of your visual fields. So if I have damage in my right parietal cortex, my left visual field will be impaired such that there is no reflexive attention. So if I'm eating food, I will not eat half of my plate, the half of the plate that is opposite to the lesion, the contralesional visual field, or the left side of my plate in this example. I won't even pay attention to it, and so that food will be uneaten. If someone comes in and tells me like, hey, you only ate half your food, pay attention to the left side of your plate, you can voluntarily move your attention over to that, and then you'll see that you have more food. So voluntary attention is still there. If you really focus, you can move your attention over there. But if you're just kind of thinking about something else, it's absent. Fortunately, spatial neglect does heal over time, typically. Due to various functions, like the younger the damage, or the younger the participant was when they had the damage, the faster that will go. But typically, most people will come back from it, will lose the spatial neglect. And so this is called an extinction. You basically lose your deficit. It goes extinct, right? Interestingly, with spatial neglect, you can get a return of the deficit. So that is, my neglect is already gone, right? I'm a healthy individual. I go about my day as normal, but my spatial neglect will come back if I get distracted in the ipsilesional visual field. That is, if something distracts me in the visual field that was not impaired in the first place, someone waves a hand or something, my spatial neglect will return. I will stop paying attention to anything in my reflexive or in my ipsilesional visual field. So hopefully that makes sense. Okay, so that's attention. Next thing we talked about was memory. So there were three memory systems: sensory memory, working memory, long-term memory. Sensory memory is like a lingering sensory store that seems to be fairly capacity unlimited, but it only lasts for about half a second unless you pay attention to it. And then you have working memory. Working memory is a small, limited capacity system that keeps information that's useful in the current moment, and it's used for behavior. It's what we work with, which is why we call it working memory. So limited capacity, limited amount of time. It doesn't last for all that long, maybe 12 seconds at max. And that's what we use for behavior. And then we have a long-term memory store, which is long in both duration and size. So it's unlimited capacity and pretty much unlimited time. So those are the three major memory systems. All right, so then we talked about the neuropathology of memory, or at least the most famous one, which is amnesia. So this is typically found in individuals who have lesions in the medial temporal lobe. So if you damage the medial temporal lobe, typically participants will be unable to collect new memories. They can remember childhood memories, no problem, but they can't collect new memories. So this is what we call anterograde amnesia. So anterograde amnesia is when we cannot collect new memories, and then retrograde amnesia is when we can't remember things from our past. So typical typical symptoms of someone who has MTL damage is pure anterograde amnesia and slight retrograde amnesia. That is, they can't remember what happened right before the incident, but like they can remember their childhood memories and that sort of thing. Okay, then we talked about how is it that we retrieve memories from long-term memory stores. So it seems that there's actually two retrieval mechanisms, one called recollection and one called familiarity. So recollection is what you think of when you think of retrieving memory. So I ask you, what did you have for lunch? And you can bring that up. I say, oh, I had noodles for lunch. I can remember exactly what I ate. So that is recollection. I'm recollecting exactly what I saw. Familiarity, on the other hand, is just that you know that you saw it, but you just can't quite get the rest of the information. So I know that I know what I had for lunch yesterday, right? I remember I had something to do, like the word started with an N, but I can't just quite get the information that I actually had noodles. So it's this continuous graded in strength, like I know it a little bit, or I'm really sure that I know it, I just can't quite get it. But it does seem to be actually a separate system entirely that's doing that. So knowing that you know something is different than actually getting the information and recollecting it. And so the remember versus know paradigm is how we typically study that. It's basically a recognition task where you have two responses. You know that you saw it, or do you actually have the memory of having seen it? And then we find that the hippocampus is involved in recollecting things. So recollection is in the hippocampus, and then familiarity seems to be in the gyrus that's just inferior to the hippocampus, which is the parahippocampal gyrus. And then we talked about how there are different types of memory in long-term memory, non-declarative and declarative. In declarative memories, you have two types, episodic and semantic memories. Episodic are for episodes in your life. Semantic is for facts, like 2 + 2. And then in non-declarative memory, we have procedural memory and priming. Procedural memory being something like skill building or like riding a bike, like muscle memory. And then priming is when you see something, maybe even unconsciously, and that changes your behavior on something at a later time. But again, you're unconscious of that happening. So it is a non-declarative form of memory. And in particular, it's important to know that amnesia only affects episodic memory. So amnesic patients can't remember what they had for lunch, right? They can't remember that actual episode, but they can tell you who the current president is, that sort of stuff. Okay, and that's memory. Oh, right. Almost forgot. So we finished with talking about false memories and memory distortion. So false memory is our memories that are in your brain that you can recall and tell me about, but they never happened. So there's a lot of different methods in which you can kind of trick the brain into having false memories. Basically, the brain is always filling in information that it doesn't have. And so it's often creating new memories that haven't actually occurred to kind of fill in the blanks. And so those are all false memories. And so it's an important thing to remember. Okay, then we talked about knowledge. So how is it that knowledge is structured in the brain? We had talked about 3 different approaches. So you have definitional, prototype, and exemplar approaches. So if I have a bunch of categories in my brain, so like cats and fruit and dogs, those were not really related, but so let's say we have 2 categories I'll just talk about for this example, cats and dogs, and we come across a new creature and we want to figure out, is this new creature a cat or a dog? In the definitional approach, what we'll do is we'll just use the defining features of those 2 categories to see if this new creature falls in them. So the definitions of a cat would be, fluffy, it meows, has whiskers, has a fluffy tail, big eyes, that sort of stuff, right? Whereas the dog would be, it barks. It also can be fluffy, but sometimes not. It's, has a tail and that sort of thing. So you have a lot of different definitions, and you just see, does this new creature fit those definitions? The prototype approach, on the other hand, is, let's say you have dogs and cats again. you would average all of the cats that you've seen into one prototype cat. So this is like the most average cat. And this is something your brain just does. It just comes up with a prototype. And then what you do is when you encounter a new stimuli, a new creature in this case, you're comparing that creature to the prototype. So you're actually almost like visually comparing the two to see how many features they share.